Are you still in live stream?
Mason, do you know how long will be your talk?
It should not be much more than maybe an hour, maybe a little bit more, but I didn't.
Yeah, but you can go for 90 minutes if you want.
Yeah, but I didn't plan for 90 minutes.
We'll see.
Yeah, it depends how many questions.
Mason, do you want to wait for some particular audience, or maybe we can gradually start?
No, we can start. I'm ready anytime.
Yeah, people might. Well,
yeah, you can see the screen and the mouse. Everything's fine.
Yeah. So let me introduce you. Welcome everyone. Welcome to Quantum Matter in Math and Physics Seminar Series at Harvard CMSA. Today we are very happy and it's our great honor to have Nathan Benjamin from Princeton University. Nathan studied at MIT for his undergrad, and then he went to Stanford University for his PhD under the supervision of Xiaomi Kashiru. Then currently he is at the Princeton University and gradually moving to Caltech next week, I think, or next week. And today he will be speaking about his recent works, a series of recent works, relative works on the CFT, 2D CFT. Today's topic is harmonic analysis of 2D CFTs, and let's welcome Nathan. I would like to remind the audience, please feel free to interrupt and ask questions. Please take over. Thank you.
Okay. Yeah. Thanks, Juven. Thanks very much for the introduction, and thank you very much for an invitation to speak here. So, yeah, as Juven said, please interrupt anytime. I might not see the chat, so just interrupt. So the title of this talk is Harmonic Analysis of 2D CFTs, and a lot of what I say will be some review of previous works, but to the extent that I say anything new, most of it will be based on this paper, which appeared a few weeks ago with these fantastic collaborators. I might touch also a little bit about some other previous work, but it'll be mostly based on this paper. And let me start by talking about just some introduction and some motivation. So the topic that this talk is going to be about is conformal field theories in 2 dimensions. And I think there are quite a variety of reasons that you might be interested in 2D CFTs. So you might be interested in critical phenomena in 2 dimensions. You might be interested in the string worldsheet. You might be interested in quantum gravity in 3 dimensions in anti-de Sitter space. And there are even some pure math applications, like you might be interested in Calabi-Yau manifolds. And all of these, you can put interesting constraints and understanding by studying general properties of 2D conformal field theories. And these theories are quite, the structure is quite intricate, and there's a lot of very powerful constraints that are available to us in 2 dimensions that are not available in higher dimensions. For example, the infinite dimensional Virasoro symmetry and also modular invariance. And this second one is going to be the key player in this talk. And we're going to ask questions about constraining and understanding possible partition functions, so spectra of the theory, using the constraints of modular invariance. There has been a lot of work done on this subject under the general heading of the bootstrap or the modular bootstrap. And in this talk, I'm going to bring in a different technology to answer these questions about, which is called harmonic analysis. And this has been used to great effect to study 4-point functions in the bootstrap community with various works. And I'll describe some similar but different approaches that we use to use this harmonic analysis technology for modular invariance. So let me give a brief sort of outline of the talk. I'll talk about, there'll be sort of 3 main themes. First, I'm going to review this technology that the mathematicians have developed, and just quite a beautiful theory of the harmonic analysis of the upper half plane. So this is the complex numbers with positive imaginary part, mod this modular group SL2Z. I'll describe applications to Narain's family of CFTs. So these are theories of C-free bosons. And this is an interesting application for a number of reasons. First, it's a nice playground to warm up with, and we'll see some very beautiful results here. And secondly, this recently has been of great interest because it's some people have used this as a toy model of holography, where if you average over these particular CFTs, there's some well, exotic 3D gravity-like theory that may be described by the average of these Neuron theories. And finally, I'll discuss general irrational 2D CFTs with just a Virasoro symmetry and a non-zero twist gap, and we'll prove some new general theorems that I don't know how to prove without this technology. And again, as I said earlier, the main strategy we're going to be using is modular invariance of the Taurus partition function. So if we define z of tau to be the one-loop partition function, where tau is an element of the upper half plane, the key player is that any large diffeomorphism of the torus, which is acted on by this group SL2Z, the group of 2x2 matrices with determinant 1 and integer entries, this partition function must be invariant under this transformation, and this is a very, very constraining property. So in some sense, you should say that this variable tau is not really valued in the upper half plane, but it's really valued in the quotient upper half plane mod SL2Z. And before I get into the details, let me just say throughout this talk, a brief word of notation. I'm only going to write it as a function of one variable, not the complex conjugate, but that's just notation. All of my functions are not meromorphic, so don't be confused by that. And I'll often use the letters x and y to denote the real and imaginary parts of the torus parameter tau. Okay, so that's a brief roadmap of where I'm going to be going. So let me start with first discussing this technology of harmonic analysis, which is where we will expand modular invariant functions in terms of eigenfunctions of the Laplacian. So first, let's review this upper half plane H. This is the complex numbers with positive y, positive imaginary part, and there's a natural SL2Z action, and a fundamental domain that we can choose for this SL2Z action is this gray region here, and this goes all the way up to I infinity. And on this entire space H, there's a natural metric which you can check is invariant under the SL2Z action, which is basically this kind of like in these Poincare coordinates, dx squared plus dy squared over y squared. And with this metric, we can define a Laplacian given here. And what we're going to be doing is looking at eigenfunctions of this Laplacian and expanding all square integrable functions in terms of these eigenfunctions. It's very, very similar to what you do in Fourier analysis on flat space expanding in plane waves. Like in Fourier analysis, there's a natural inner product that you can define on this space, which is just given by integrating over the fundamental domain with the appropriate measure times the product of the two functions. And what this measure will do is this is precisely the measure that will single out the eigenfunctions that you're interested in. So what that'll do is this will allow us to read off the basis coefficients when we decompose into these eigenfunctions. So these eigenfunctions will form some orthonormal basis with respect to this inner product. So the basic idea is that we're going to decompose all square integrable modular invariant functions into eigenfunctions of the Laplacian. Now, the structure of these eigenfunctions of the Laplacian is quite intricate and interesting. These have been completely classified by the mathematicians, and I'm going to go through what they are in detail, but let me just say very quickly that there are three types. The first is there's a constant function. So the constant is obviously modular invariant, and it's trivially an eigenfunction with eigenvalue 0, because derivatives acting on constants are very easy to compute. And there are two infinite families. The first is there's an infinite continuous series that are sometimes called the real analytic Eisenstein series. And these are labeled by a continuous real number. And then there are an infinite discrete series of eigenfunctions, which are sometimes called mass cusp forms. And these are labeled by some positive integers. So there's 1, 2, 3, 4, 5. And one analogy you can think of is these are kind of like your plane waves in some Fourier analysis. And these second ones would be more like some bound states of some quantum system. So some energy eigenvalues that are some bound states.
Nathan, a quick question here.
Yeah.
So in practice, I guess we will then talk about Taurus partition function of some CFTs or ensemble average thereof. Do we expect those functions to be square integrable?
No. So I'll discuss this. I'll discuss this more. So indeed, very good. Okay. Yeah, very good. This technology is not going to completely apply to partition functions because they are very much not square integrable. So I'll discuss this. I will discuss this briefly how we'll get around this. But right now, I'm just going to tell you this math fact, which is that these square integrable functions can be decomposed into these eigenfunctions of the Laplacian, and then we're going to have to work a little bit harder to get this math fact applied to the physics setting we're interested in. But that's an excellent question.
Okay, thank you.
Okay, very good. So okay, good. So let's talk about these two more interesting eigenfunctions in a little bit more detail. So the first is these Eisenstein series, and they're defined very simply.
Sorry, Nathan?
Yeah.
Just to be sure, so when you say square integrable, you mean square integrable with respect to this this measure that you just defined?
Exactly. So I'll define it later, but it just means that if I take some function f mod squared with this measure integrated over this keyhole region, that it should be finite. And indeed, partition functions, as Shohang alluded to, are very much not that because of the Casimir energy of the vacuum. But I'll say all that later. So yeah.
Thank you.
Very good question, though. Okay, so we're discussing right. Good. So the first type of these eigenfunctions are these real analytic Eisenstein series, and these are defined very simply. They're in some sense the simplest modular invariant you can write down. But you start with the imaginary part of tau raised to some s power, and then you sum over all SL2Z orbits of this guy. By definition, this is modular invariant because we're summing over the entire modular group. Moreover, if you sort of stare at this expression long enough, you can convince yourself that for convergence, you need the real part of this parameter s. So this parameter s is any complex number, but you need the real part to be bigger than 1. However, it turns out that this function admits an analytic continuation to all complex s. And the analytic continuation is, I think, most easily understood through the Fourier expansion. So because this function is modular invariant, it can be expanded into spins. And it has the following Fourier expansion. So, okay, the details don't matter, but I just want to point out a couple of things. First of all, there's a scalar component here. And then there's all of the spins are present. So j equals 1 is the spin 1, spin 2, spin 3, etc. You can look at this expression and you can convince yourself, and well, by definition, that this expression is modular invariant because it comes from this sum here. And moreover, it's very easy to see that this is an eigenfunction of the Laplacian, because every individual term in this sum is an eigenfunction of the Laplacian. So if you take this Laplacian expression, dx squared plus dy squared over y squared, and you look up some facts about Bessel functions, you'll see that each individual term of this is already an eigenfunction of the Laplacian. And the magic is that when we combine them in this particular way with these divisor sigmas and blah, 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 that this is then completed to a modular invariant function, which means that it's valued not just on H, but on H mod SL2Z. So, and the eigenvalue is S times 1 minus S. So if we were just doing harmonic analysis on H, rather than on H mod SL2Z, any individual one of these functions for any j, or this scalar sector, would be a fine eigenfunction. However, because we want it to be valued on the keyhole region rather than the whole upper half plane, we need to sort of combine them together in a way such that we can define this function only on this keyhole region. And this is one such way to combine them. Okay, so these are the Eisenstein series. And now I'm going to describe the other type of eigenfunctions, which are called cusp forms. So first, just the reason of the name, the word cusp, this is just a word that mathematicians use, which means that there's no scalar sector, and this function decays very rapidly at the cusp. Okay, so I'm going to denote them as nu sub n, where n is some positive integers, and these are some discrete eigenfunctions. They're modular invariant, and they take the following form. So first, I want to say a couple of things. So first, note there's no scalar, as I promised. And also, the functional form in terms of x and y, which are the real and imaginary parts of tau, is exactly the same as we saw here. There's again this cosine 2 pi jx squared of y times a Bessel function. That's not a coincidence, because indeed, as I said earlier, this combination here is precisely an eigenfunction of the Laplacian. And indeed, if you wanted to solve this differential equation, that you just want to be a Laplacian on H on the upper half plane, then this is the solution that you would get. However, we now need to build them and combine them in a way that's modular invariant. And now it's actually much, much more difficult to do so than in the case of the Eisensteins. And it turns out that for most values of this index of this Bessel function, there will not exist a solution. There only exists a solution at random, discrete, sporadic values, R sub n, which is related to the eigenvalue by this expression here. Moreover, there's a bunch of real numbers, aj of n, that you have to solve for. And there's no known closed form expression for these. These are conjectured to be random transcendental numbers, and it's only known how to compute these numerically. So these aj of n and rn are some sporadic real numbers, and their statistics are very, very interesting. I'll discuss that a little bit more later. Of course, it's an eigenfunction, so I can rescale it however I want. And I'm going to use the convention where I take the spin 1 guy and set it to be 1. Obviously, I can rescale an eigenfunction however I want, and that's the convention that I'm going to use. And it turns out this is actually quite a natural convention from many ways. As a technical point, this convention is not natural in the sense that under this norm that I defined, these cusp forms do not have norm 1. But that's fine. I mean, we can deal with that. So let me just give you a little bit more intuition, or just a feeling of what these cusp forms are like. Here I've written down the first 5 cusp forms. So recall the functional form depended on some parameter r sub n, a real number, and then infinite sequence of real numbers, which are just some real numbers multiplying the spin j coefficient of this modular function. And here are the first 5 of them. So you see these are just some random numbers. Here are the eigenvalues. I normalized the first coefficient to be 1, and the rest of these are just some random numbers with some interesting distribution. You can check numerically that if you keep enough of them, you can get something that's modular invariant, but there's no known closed expression for any of these numbers. So mathematicians are very, very interested in the distribution of these eigenvalues and their statistics, and they've actually computed these numbers numerically to a lot of precision. So just for fun, this isn't going to be particularly relevant, but just for fun, this is a paper from 2006, about 15 years ago, by Brooker, Strombergerson, and Venkatesh, called Efficient Computation of the Mass-Cost Forms. And I just want to point out the second sentence in the abstract. They computed to over 1,000 decimal places, these eigenfunctions. And just for fun, this is a screenshot of a part of their paper. So they really do care quite a lot. And these functions are well studied in the math literature. Okay, so just to recap this math fact, the statement I was saying is that the Eisenstein series, which have this continuous parameter s, if you take it to be along the principal series, meaning s is 1/2 plus I times a real number, together with these cusp forms, as long as the constant form an orthonormal basis for all square integrable functions on H mod SL2Z. So for all modular invariant functions that are square integrable. By square integrable, this is what Ivan asked a couple of minutes ago. By square integrable, I mean that the function squared under the appropriate measure is finite. And just to drive home the point, so this is sometimes called the Rolle-Selberg decomposition. If f of tau is any square integrable modular invariant function, there is a unique decomposition into the constant, the Eisensteins along the principal series, and these Mas-Cusp forms, and their coefficients are just given by this Peterson inner product. So the inner product that we all studied in quantum mechanics of just integrating the function against the basis vector, complex conjugate with the appropriate measure. I divided by these values because I choose to use a basis where the basis vectors are not uninormalized. The advantage of this decomposition is that this is a decomposition that is manifestly modular invariant. Suppose someone were to hand you a decomposition like this, like the form here. It is completely obvious that the left-hand side then is invariant under SL2Z because it is written in terms of basis vectors that are all invariant under the modular transformation. Let me contrast this to the usual decomposition that we do in CFT when we decompose a partition function into the characters, or similarly, a 4-point function into its conformal blocks. So if we take a partition function of a CFT, we'll decompose it into the characters of the chiral algebra. For example, suppose the theory has Virasoro symmetry. Then we'll decompose it into the Virasoro vacuum character, which is a known function that you can look up in Di Francesco or whatever, and all of the massive characters. And they'll have some degeneracies, which are positive integers, which is counting the dimension of the Hilbert spaces with those quantum numbers. Under this decomposition, modular invariance is completely miraculous because each of these characters under modular transformation transforms into some complicated continuous decomposition of other characters. And somehow miraculously, although each individual character or any finite number of characters does not give anything good under modular transformation, all infinite characters resum and give you the same thing under any SL2Z transformation. However, under this decomposition, unitarity of the theory and discreteness of the theory is completely obvious because you just look at this expansion and you look at these numbers and you check that they're numbers like 7 and 6 and not -3 or pi. Juven, yes.
Yes. Hi.
Hi.
So naive question. Just want to make sure. So how is this mass-cusp function, this nu of tau, and also the Eisenstein series ES of tau helps to write down the partition function? I kind of not directly understand. Maybe I just missed.
Yeah, very good. So this is what I'm saying here, which is so I haven't related that yet because there's some subtleties that Shuheng brought up, which we'll address. But the idea is that roughly speaking, what I'm going to be doing is I'm going to be decomposing the partition function in an alternative way. Instead of decomposing in terms of the characters, I'll decompose it in terms of these Eisensteins and cusp forms. And there's an advantage and there's a disadvantage. The advantage is modular invariance is manifest. The disadvantage is unitarity is not manifest. And sort of the philosophy of this talk, or the hope, is that we'll learn different things with this sort of like dual basis in some sense. So the usual basis that we decompose it is in characters of the algebra, and there unitarity is manifest, but modular invariance is not. And by imposing constraints of modular invariance, then there have been beautiful papers written where we've learned about like the size of the gap and other constraints of the CFT. And now the philosophy of this talk is I want to look at a different basis where now modular invariance is manifest, but unitarity and discreteness is not. And I want to use constraints of the latter to learn interesting new theorems about the space of possible CFTs. And then what we're gonna, and then so that's the big picture philosophy. And then we'll in the second part of the talk, I'll do some explicit examples of some Narain theories and then some general CFTs.
Okay.
Oh yeah, thanks for the question. That's a very good question.
And by the way, just make sure. So what maybe the type of the class of a CFT you will explore? Just maybe, for example, are there certain limitations on certain CFT you are exploring in 2D by this?
Yeah, very good. So I want it to be I want the CFT to, I guess, obey the usual axioms like modular invariance and unitarity and discreteness. And I want to have, well, actually, I will not really use this, but let's say I want it to be to have a discrete spectrum and have a unique SL2R invariant vacuum.
And it's also fundamentally bosonic in the sense it does.
Very good. Oh, I see. Yeah. I'm going to study bosonic CFTs. Actually, I haven't done this, but I suspect it's very, very easy. If you ask me about if this can apply to fermionic CFTs, is that the question? Yeah.
Also general class. Maybe, yeah, this is one aspect. Yes.
I suspect it should be very easy to modify this for fermionic theories. What you would do is not harmonic analysis of H1 SL2Z, but one of these index 2 subgroup or index 3 congruent subgroups of like gamma naught of 2 or something like this. So I suspect it should be very easily modified to look at these fermionic theories, but I haven't done that. But yeah, thank you.
Thanks.
I have a maybe a rather vague question. So if I were to draw an analogy with the 4-point function,
right,
CFT, and well, in usual 4-point function, we can expand it on conformal partial waves. Mm-hmm. And then there's also some continuous, principal series.
Absolutely.
But that, as you mentioned earlier, in that expansion, crossing symmetry is not building. Right. So if I were to draw an analogy, is it more similar to the Melling space?
Yeah.
To the Melling decomposition, or?
Yeah, I think. These conformal partial waves is very similar in the sense that those are like some eigenfunctions of some Casimir.
Yes, the crossing is not building.
Right. But the crossing symmetry is not built in. I think that that might be more analogous to doing harmonic analysis on H rather than on
exactly.
H mod SL2Z. And the advantage is that that both that and this have is that there's some sort of inversion formula, which is precisely this this inner product right here, right? Because then you can easily read off this basis vector from doing some kind of inner product. It's kind of interesting. I actually don't know of any, for example, I don't know of any analogy of these cusp forms. And it's because these cusp forms only show up when you're not just doing harmonic analysis of H, but H mod SL2Z. Right. So you need to combine these eigenfunctions of H into a function that can be defined on this keyhole region. So I think there is some analogy, but I'm not sure if it,
But then I wonder for the ordinary 4-point function, can one mod out do that quotient explicitly?
Yeah. I kind of wondered this. I haven't tried it, but I think it would be quite interesting. For example, as a warm-up problem, I think if you look at 4 identical scalars, then like you can just do some coordinate change and rewrite the crossing equation in terms of the modular transformation.
Right. Yeah.
So I think that this technology should, in principle, be able to be applied to that as well. Again, you have to worry about the square integrability stuff, but that can be dealt with. Well, I'll say it later, but since you asked it, what we just do is there's only a finite number of operators that make it not square integrable, which are operators that are lighter than C over 12 roughly.
I see.
So you just subtract out the Poincare sum.
I see.
Something like
I
this.
see. Okay, thank you.
Yeah, thanks. Yeah, very good question. Okay. Very good. So as Juven asked, how is this decomposition useful for CFT partition functions? And now, as many people and like Shuhong alluded to, there's a big problem, which is that there was something that I tried to shove under the rug, but you guys called me out on it, which is that the theorem, this math theorem that the mathematicians promised us, only applies to square integrable functions. However, partition functions are not square integrable. So here's a very simple reason to see why. So let's assume my function f has no poles other than at the cusp. That's a very reasonable assumption for partition functions, because that's for partition functions, that's saying that at any finite temperature, the partition function should be finite. So there shouldn't be like a Hagedorn transition. So that's a very reasonable assumption to make. And if you make this assumption, then this is true if and only if you sort of only have to worry about the behavior of this function f at very large y, because everything else is finite. And what you need is that at very large y, the function grows smaller than square root of y, right? Because you see that if it grows as square root of y, you get a logarithmic divergence. So anything square root of y or bigger or faster at large y gives you something that's not square integrable, and anything slower than square root of y is good. And partition functions at large imaginary part of tau are much worse than square root. They're much worse than polynomial. They're exponentially divergent because of our Casimir energy. They in general do not have a decomposition in terms of these eigenfunctions, and we'll have to work harder to get them this. So we're going to get around this problem. First, we're going to, as a warm-up, get around it for a special class of theories called the Narain theories, and then we'll apply it to general irrational theories with just Virasoro symmetry. The rough idea is that there are only going to be a finite number of states that are badly behaved that give us this exponential divergence, and so we're going to remove them in a controlled way that preserves the modular invariance, and sort of we know exactly what we remove, so we can add it back in at the end of the day. Okay, that was the general picture of this technology, and now I'm going to apply it to Narain theory. So maybe now is a good time to stop for questions, although of course you can interrupt me at any time. Okay, very good. So let's start with everyone's favorite theory, which is the C=1 free boson. So this is maybe one of the first CFTs that we study. It's in chapter 2 of Polchinski. So this is just a free theory. There's a bosonic field X, which we're going to take periodic with some periodicity R, which is a parameter of the theory. That's going to be, I'm going to call that the radius of the circle. And the action is just this quadratic action. So this theory is free. It's exactly solvable. You could compute all correlation functions and the spectrum. And I'm just going to tell you what the answer is. So the partition function is given by the following. So I'm going to label it by the worldsheet parameter tau, and also what I call the target space parameter R. So this target space parameter labels like which C=1 theory you're discussing. So there are many C=1 theories depending on what the periodicity condition of this field X I pick. And this target space coordinate R is going to label that. So these coordinates kind of are on different footing. This is a worldsheet coordinate. This is a target space coordinate. And the partition function is just given by this expression here. It's not so complicated actually, but what happens is this function here, this is called the Dedekind eta function, which I defined here. And this is just the integers partition function. And it's just counting all of the bosonic oscillator modes. So it's counting words you can make with these oscillator modes coming from the free boson. And then there are some non-trivial momentum and winding modes that you can get from some wrapping, the string wrapping the circle several times, or some units of momentum. And if you compute the energy and the momentum of these modes, you'll get the following infinite sum. And this is sometimes called a theta function. So the sum here, n and w, go over all integers. One thing I want to note is that there's an interesting symmetry where I take the radius r to 1 over the radius. And the units work out because there's a parameter alpha prime, which I've suppressed. So there's an interesting symmetry, which I'm going to call T-duality, which takes the radius to 1 over the radius here. So this is the partition function of one free boson. once you do one free boson, it's not difficult to consider C different free bosons. And so the action is here. It looks complicated, but it's actually very simple. So here, P and Q are indices that go from 1 through C. So they're what I'll call the target space coordinates. So GPQ is just some C by C matrix. It's just some coupling constants from the two-dimensional theory. And this alpha beta are the worldsheet coordinates. So these run from 1 to 2, the two-dimensional quantum field theory space-time coordinates. This is just the most general action you can write down, because you can have a symmetric combination and an anti-symmetric combination. And if you count it out, there are C squared total coupling constants that you can tune, and each one of these gives you a different conformal field theory. Again, you can compute the partition function. It's just free field theory. And I'll just tell you the answer. Again, there are these oscillator modes. Now there are more of them because you've got more bosons. And this part is sort of the same no matter what point in the moduli space you are, which I parameterize by these G and B. However, again, there's some non-trivial lattice theta function coming from the non-trivial momentum and winding modes. And if you are careful and work out the energy and the momentum, you'll get this expression for the full partition function. So the details don't really matter. I just want to point out that there exists a expression, and all of the interesting moduli dependence is in this theta sum here, because this is just the oscillator modes and it's the same at all points in the moduli space. You can check that this partition function is invariant under SL2Z, acting on tau, as it has to be, because it's a well-defined compact CFT. But there's also an interesting T-duality on the target space, which if you work it out, if you act on these G and B fields with this discrete group called OCCZ, this gives you an interesting symmetry of the target space, which is called T-duality. So I'm just bringing this up because it's going to make an appearance again when we study these Narain theories in a little bit more detail. So these partition functions have the same exponential divergence that all CFTs do from the vacuum Casimir energy. But I'm going to instead of decomposing this full partition function, I'm going to soak up these oscillator modes. So I'm going to rescale this partition function by this function eta to the 2c. However, for those of you who have studied modular forms, you'll know that spoils the modular invariance, but it's very easily fixed. It turns out by an additional power of y, the imaginary part of tau. So we're not going to be decomposing the full partition function, but rather the lattice theta function, which I'm going to be defined as the partition function with the oscillator mode soaked up, and this additional guy, which is just necessary to restore the full modular invariance. So for those of you who are experts, this guy has a weight, and this has precisely negative the weight that this eta function has. So they precisely cancel out. And this combination here is fully modular invariant. So this has all of the same information as the free boson, but it's a tamer function to study. So this function is going to be y to the c over 2 times the lattice theta function. So now we've made progress. At large y, instead of growing exponentially, now we grow polynomially. Unfortunately, it's still bigger than the square root of y required for square integrability. So this function we can't quite yet apply our technology to, but we're very close. What we're going to do is we're going to subtract out a term that grows as y to the c over 2. And there are various ways of defining what the term we're going to subtract out is. The first thing I can say is that the term we're going to subtract out is an Eisenstein series at s equals c over 2, which we defined earlier. And that's a modular invariant function, which you can check has the right growth properties. So just mathematically, we're allowed to subtract this from the partition function, and we'll get something that is square integrable. However, there's actually a very, very interesting physics interpretation for what we're subtracting. It turns out that this function that we're subtracting, which is the modular sum of the vacuum state, the vacuum state in this lattice theta function, has an interpretation as the average partition function of the C-free bosons theories. So what we're going to decompose is the deviations of the Narain theory from the average. So let me say that again. It turns out in a series of 2 beautiful papers from about a year or 2 ago that the average of C-free bosons was computed and considered as a toy model of holography in the context of ADS3 CFT2. And what these gentlemen showed was that the average partition function of C-free bosons is given by this Eisenstein series, E sub c over 2. So this is just some function, it's modular invariant, and it's defined as the modular sum of y to the c over 2. This isn't going to be that relevant to the talk, but it's quite interesting. So I just want to say that this sum over SL2Z was interpreted or conjectured to have some gravitational interpretation as a sum over classical geometries, where each term in this sum labeled a different classical geometry with the same conformal boundary. And this term in this summand was interpreted as some Chern-Simons-like action. So it was considered some sort of toy model for ADS CFT, where the average of a bunch of CFTs was given by some gravitational gravity-like theory. Now, for our purposes, the holographic interpretation will not right now be important, but the interpretation of as an average gives us a nice physical interpretation. What we're going to be decomposing is not the partition function of C-free bosons, but rather the deviations of that partition function from the average, and that has good spectral properties, and will have very interesting properties as we will soon see. Okay, there's any questions on that before? So I'm now going to do a couple of examples at small c. So maybe now's a good time for questions.
Sorry, I think I'm missing something basic. So why is it sufficient to subtract EC over 2? Is there any other intermediate terms? Some other power of y?
Oh, very good. Good, excellent. The answer is no. It's because yeah, I didn't say that, but you do need to check that. So let's look at this sum here. So let's look at when n and m are both. So we need to sum over these c vectors. Let's look at when n and m are all 0.
Yeah.
So then this term is 1. So then you get this y to the c over 2. Right, but now let's look at, so that's just one term and that's the vacuum. Now let's look at any non-trivial momentum winding sum. So n is like 1, 7, 6, whatever. Now this will be e to the minus y times some energy.
That will be
exponential. And now you win. Now you win so much because it's e to the minus y. So then
I see. Thank you.
Yeah, that's a very good question. Okay. So now let's do this explicitly for c equals 1 and c equals 2. And then I'll write the general C formula. The reason I want to do c equals 1 and c equals 2 explicitly is a couple of reasons. One is that we'll be able to write down quite beautiful and interesting formulas, but also these cases are a little bit special because these are the only two cases where the average of these three bosons is not completely well defined. And the reason is that these Eisenstein series have some, if you remember, I said that they only converge when this parameter here is bigger than 1. So these defined via analytic continuation. And it turns out that it has a 0 when c equals 1 and a pole when c equals 2. So for c equals 1, that actually makes our life very easy because that means that when we subtract out this e sub c over 2, we're subtracting out 0. So we actually don't have to subtract out, we don't have to subtract out any average. And actually, even though there's a logarithmic divergence in the norm of the c equals 1 partition function, it turns out that we don't need to subtract anything to have a good spectral decomposition. That's not a contradiction because the mathematicians didn't promise us an if and only if. They just said that if the partition function is in L2, then we can get a good a spectral decomposition. But the converse may not necessarily be the case. So to do the c equals 1 spectral decomposition, there are only 3 integrals we need to compute. So recall the basis vectors were the constant, the Eisenstein series where s has a real part at half, and then these weird cusp forms. So we just need to compute these 3 integrals and then we're done. So I'm not actually going to go through these integrals in detail because it's a little bit technical, although I'm happy to discuss in any more detail. I'll just tell you the general strategy that is used to compute these integrals. And it's there's a very beautiful trick called the Rankin-Selberg transform, which is used to compute these integrals. And the basic idea, it's funny because this trick has this very fancy name, but it's actually a very simple and beautiful trick. The basic idea is that if one of your integrands can be written as a sum over SL2Z images, which I'm sometimes going to call Poincare sum, then we can rewrite the integral. So imagine that one of your integrands can be written as a sum over SL2Z, and the other is just some function. Then what you can do is you can move the sum over here, and instead of integrating over just the fundamental domain, you're integrating over all SL2Z images of the fundamental domain, which is the upper half plane itself. Or if, and then there's some tricks where maybe you integrate only over the strip instead of the whole upper half plane. But then the idea is that integrating over the upper half plane or over the strip can be much, much easier on a technical level than doing the integral over this fundamental domain, because this fundamental domain is weirdly shaped. So there'll be weird like boundary condition effects and stuff. But these integrals in practice can be much simpler. So this is just a mathematical trick, but I just included it in case people are interested. And it turns out that we can use this trick for the Neuron theories. We can rewrite the theta function by some Poisson ring summation, and we can write it as some Poincare-like sum. So okay, the details don't really matter. The only punchline is at the end of the day, we're able to do these three integrals, and I'll tell you what they are. So the integral with the constant gave us this term r plus 1 over r. So that has to be multiplied by a constant. If you work hard and compute the integral with the Eisenstein series, you get this function here. So some zeta and gamma functions times r to the 1 minus 2s plus r to the 2s minus 1. And finally, these cusp-forms are very complicated, but it turns out you can still do this integral analytically using this trick, and it vanishes for all c equals 1 theories. So there are no cusp-forms. So the final decomposition of the c equals 1 Narain theory is this expression here. And I want to study a little bit the interpretation of the overlap functions. The first thing I want to note is that this is manifestly modular invariant, but it's also manifestly T-duality invariant. If I take the radius to 1 over the radius, this term is obviously invariant, and this term is obviously invariant. This is not a coincidence, and I'll explain it shortly in the next slide. The second thing I want to emphasize, as I said at the beginning of the talk, is that from this expression here, the fact that the spectrum is discrete is completely not it's completely hidden. It's not obvious at all that this is a discrete spectrum. And I'll say a little bit more about that later.
Nathan, just to be sure. So the way you show that this discrete, the mass forms does not show up is to use the property for the Laplace equation. Property of the eigenvalues of this news under the Laplace equation.
Yeah, and in fact, there are other properties of these news that you can use. Like there are other operators called Hecker operators that there are eigenfunctions of that for higher C that we may need to use to compute this integral explicitly. But for C equals 1, all we need to use the fact actually is that it doesn't have a scalar sector. Later for C equals 2, I'll need to use other properties of it. But yeah.
Okay.
Okay, so here's the formula again, which I reread above. And so let me just remind you, we decomposed it into eigenfunctions of the Laplacian on the worldsheet moduli space. The worldsheet moduli space is just H mod SL2Z, and its eigenfunctions are ES of tau, the constant, and this discrete guy mu. So now you can ask, is there any interpretation of the target space moduli space? So recall that at C equals 1, the target space is just labeled by this parameter R. And there's a very natural metric called the Zomological Metric coming from considering the 2-point function of two marginal operators. And if you just compute it, this metric is dr squared over r squared. And okay, you can check that this metric obeys the T-duality r to 1 over r. Okay, so just for fun, let's look at the Laplacian, the eigenfunctions of the Laplacian of this space. This has the following Laplacian, and then if you just put this in, solve the differential equation, it has the following eigenfunctions: r to some number plus r to that negative number, and the eigenvalue is s minus the half squared. So you'll notice that this and this are precisely the same. So what we've done is we've taken the c equals 1 partition function, lattice theta function, and decomposed it into correlated integrals of correlated eigenfunctions of target space and worldsheet space. This isn't a coincidence. There's a reason this had to be the case. So there's a very simple calculation that shows that the Narain lattice theta functions obey this following differential equation, where roughly speaking, the worldsheet Laplacian and the target space Laplacian are the same up to some numerical constant. And this was first discussed in some beautiful work by Obers and Killian. Let me say some intuition for this differential equation. The intuition is actually very simple. So what does the Laplacian on the worldsheet do? That's like taking some derivatives with respect to your modular parameter tau. So that's like pulling down some factors of the stress tensor. Because if you take some derivatives with respect to tau, you're pulling down factors of L naught. However, the Laplacian on the target space is like moving around in the conformal manifold. So you're like pulling down factors of your marginal operator. But for the Narain theories, the marginal operator is just J squared, your current squared. And for the Narain theories, these are the same thing. The current is pure Sugawara. T is just J squared. So there should be some relationship between the Laplacian on the worldsheet and the Laplacian on the target space for these specific, very special theories. And if you work out the details, they're related by this numerical factor here. So you'll notice if I plug in C equals 1, this factor is equal to 1/4, 1/4. And indeed, this eigenvalue here, S times 1 minus a half squared, differs from the eigenvalue here, which is S times 1 minus S, by precisely 1/4.
Do this intuition and this differential equation extend to higher genus worldsheet?
I think it should. Let me see.
Because in the intuition, you didn't assume the worldsheet to be genus 1, right?
I think there's an analogous one for prodigies. By the way, there should be an analogous harmonic analysis for like SP4Z or SP2GZ as well. Right. But I'm not sure if it's ever been, I haven't even seen this worked out in the math literature, like the harmonic analysis of this Eigen space, but I think that would also be very interesting to understand. And then if you do, I think something similar should go through.
Mm.
Okay. Okay, so let's get more intuition and work this out at C equals 2. So at C equals 2, there are 4 marginal operators now because there's 2 dx's on the left and 2 dx's on the right that we can choose. And it turns out that there's some accidental isomorphisms. And it turns out that the C equals 2 target space moduli space is isomorphic to 2 copies of H mod SL2Z. This actually is very simple to understand because let's look at what the target space at C equals 2 is. These 2 moduli are just the complex structure modulus of the target space or torus, not the worldsheet torus, but the target space torus, and also the Kähler modulus of the target space torus, where we do the usual complexification where we add this B field here. And then T duality acts as 2 independent SL2Z transformations on either rho or sigma. This was first discussed by, I think, Dijkgraaf, Verlinde, and Berlinde in the 80s, to my knowledge. So a C equals 2 partition function, we're going to label by three parameters: the worldsheet parameter tau, and then 2 target space parameters rho and sigma. And although they have very different origins, they have the same symmetry. Each of them is invariant under a different SL2Z transformation. Actually, rather remarkably, this function has a miraculous triality symmetry, where it's invariant under any exchange of these 3 moduli, which is first discovered here. The exchange of rho and sigma is a special case of mirror symmetry, where we exchange the Kähler and complex structure modulus. But the exchange of the worldsheet and the target space moduli is very mysterious, and I don't have a good. I don't know if there's a good explanation for it.
Naive question, sorry.
Yes, please.
This rho is equal to b plus I square root of determinant G. This
yes.
b, what's the range of the b? Is it real?
Yeah, this is some real number. Yeah. And yeah.
What does he specify?
Yeah. So remember in this, let me show you the Lagrangian. So this is the Lagrangian here. So let's take C equals 2. So that means that this B is in general an antisymmetric C by C matrix. But if C equals 2, of course, the antisymmetric matrix is just a number. So that's this B here. It's this term in this action where I take this dx, this term of the action with an antisymmetric contraction.
Okay, so the B and G follow directly from this Lagrangian.
Exactly.
And G is symmetric. B is
symmetric. B is antisymmetric. Exactly. Yeah. So they have some interpretation. Well, yeah, from the 2D perspective, they're just coupling constants, indeed.
But B is a matrix layer, and when you take a B in this.
I'm sorry. By B, I just mean the component of the matrix.
Okay.
Yeah.
All right. Thanks.
Yeah,
so
of course.
Rho also have some index.
Rho has some index. What do you mean index?
Like a B also have this B PQ.
Oh no, because very good. Sorry. So let me find it again. So this is by PQ I mean I'm specifically referring to C equals 2, which means that the only 2 by 2 antisymmetric matrices are just 0, B12, negative B12, 0, and I define B12 to be B.
No problem. Thank you.
Yeah. No. Thank you. Thank you for clarifying that. I should have been more. Yeah. Yeah. So indeed, B should say B12, but I was just very lazy. Okay, yeah, thank you for the question. So now again, we can compute the spectral decomposition of the C equals 2 partition function using the same trick. Okay, now before I do that, let's just try to guess what the answer will look like. Well, first, recall that again, we need to deal with this problem of square integrability that we discussed, this partition function will diverge like y to the C over 2. So it'll diverge linearly in y, and we need to diverge slower than square root of y. So we need to subtract out this Eisenstein E sub C over 2. Interestingly, this is only going to happen at C equals 2. There's a pole. However, fortunately, mathematicians have defined a regulated version of this pole, which is just defined as, I call it E1 hat, which is just the limit of E sub s minus the pole at 1 over s minus 1. So there's just a simple pole that's independent of tau. This is very sort of fortuitous for us. And this is just a technical point here. So once we subtract out this E1 hat of tau, now we need to obey the differential equation, which says that the eigenfunctions are going to have correlated eigenvalues between the target space and the worldsheet space, and we need to obey this triality. Now recall that the target space eigenfunctions are just going to be products of the worldsheet eigenfunctions, because the target space moduli space is just 2 copies of the worldsheet moduli space. So with that being said, let's look at the answer and then we'll stare at it a little bit. Okay, so this formula is a little bit complicated, so I'll go through it a little bit carefully. So the C equals 2 lattice theta function is given by the following decomposition. Okay, first alpha is just a constant, it doesn't matter. Okay, so you can compute this number, whatever. But first here's the E1 hat of tau, which I subtract out, so I can move this to the left-hand side in order to make the function square integrable. And after I subtract this out, there's a constant piece, which is these 3 terms here. They're constant with respect to tau, but you'll notice that there's an E1 hat of rho and an E1 hat of sigma, which are necessary for this triality condition here. The overlap with the Eisenstein series, E sub s of tau, the differential equation and the triality will force that the rho and sigma dependence to be precisely E sub s of rho times E sub s of sigma. And then there's some prefactor you can compute. And finally, previously in C equals 1, the cusp forms did not show up. The cusp forms, recall, were these very complicated, these infinite sums of Bessel functions multiplied by complicated transcendental numbers that the mathematicians have computed to thousands of decimal places. And it was rather lucky of us that at C equals 1, they did not show up because they're complicated. But they do show up at all other values of C. And the simplest case is C equals 2. So now the functional form is predetermined. So you have to have this mu n of tau, and the differential equation and the triality demand that the rho and sigma dependence is given by the following. Here, this is just a factor that I put here as a convention. But in principle, there could be a different real number for every different n. So for n equals 1, it could be multiplied by 6.37 and then 7. Okay, so any different, there could be a constant C sub n that's any real number, and no matter what that real number is, it would still obey the differential equation and the triality condition. Remarkably, when we compute it, all of the cusp forms have coefficient 8 when appropriately normalized. I have like no intuition for this statement. We can prove it and we can check it numerically. And I think it would be very, very interesting if there was a physical meaning of this 8, because it seems quite miraculous to me why there should be such a simple closed form expression, given that this lattice theta function is very simple. The first 2 lines are also, I mean, you know, they're complicated, but they're very simple functions to define. But these cusp forms are very sporadic and discrete and have completely arbitrary, sort of seemingly random and arbitrarily coefficients, and yet there's such a simple closed form expression for them in terms of the C equals 2 partition function. So I think this would be extremely interesting if there was something physical that this was counting, but I have no idea what that would be. But let me just,
Nathan, just to be sure, what is the full the duality group? It's just the permutation semi-direct product with the three SL2Zs?
Yeah.
Okay. Yeah, I was trying to see if this 8 is a non-trivial character for some representation of your duality.
Like if they fit inside. I think we discussed this before, but I don't think they fit inside some genus 2
not necessarily
or something like this. Yeah.
So
that would be quite interesting.
Yeah, natural place, one can look for this kind of triality invariant objects is to go to 6 dimensions and compute consider a self-dual tensor on the 6 torus. But I don't know how you can
I see.
Why C2 is special.
Well, actually, okay, that's interesting. Maybe I can ask you more about this later.
Yeah, in that case, I mean, this is just a very vague idea. You need to consider some kind of twist because naively you have more moduli than you need because you only want 3 moduli. But you do see 3 torus, which is somewhat natural. Yeah. Anyways. Yeah.
I see. Okay, no, thank you. Yeah, okay, I don't have any comments on that, but that's quite interesting. Thank you.
I have a maybe more physical.
Yeah, go ahead.
Comment on. So this system is C equal to CFT, which means there are 2 left moving and 2 right moving central charge, respectively, both are 1 + 1 and 1 + 1, right? 2 left moving mode, 2 right moving mode.
Yeah, sure. There's a U1 squared on the left and U1 squared on the right.
All right. So these are just some Luttinger liquids in condensed matter with 2 left moving, 2 right moving. Are there some? I'm just bringing this up because maybe Subirs here can make some comment. Are there some triality or whatever you described earlier in that type of systems?
Well, Juven, but I think usually in the discussion of the Luttinger liquid in the condensed matter literature, people don't turn on the B field.
That's actually.
So if you don't turn on the.
But that's the off-diagonal term in the.
Yeah, so good. If we don't turn on B field, then rho will be pure imaginary.
Right.
So if you want,
then it's hard to see the.
Yeah, if you then want to see a triality, then you have to turn off the real part of sigma, which would mean that but I can actually say what that locus is. Then that'll be a 2-dimensional locus, and that locus will just be the product of any 2 C = 1 theories.
Okay. So maybe let me just rephrase. So usually condensed matter people use so-called the symmetric bilinear form of K matrix, and that's a symmetric K matrix. But here there are some anti-symmetric off-diagonal component, the B field, and that's not usually for condensed matter field 8. Yeah. Okay. Yeah, I will think about this. Thank you.
Yeah. Thank you for the comment. Right. Okay. So just as I said, the eigenfunctions are correlated. They're correlated in precisely the way that this differential equation I wrote demands. Notice, by the way, that when we wrote if you write the lattice theta function definition of this C = 2 theory, the triality is a miracle, and it does not look. The symmetry of these 3 variables does not look natural at all. But the nice thing is when we do the spectral decomposition, the triality is completely manifest, right? It's quite obvious on the right-hand side of this equation that there's a symmetry of rho, sigma, and tau. And the final thing that I think is very mysterious is that the cusp forms, although they are non-zero, they're actually, once you normalize appropriately, they're actually incredibly simple. And I have no idea why. Okay, so let me now just briefly say what the answer is at general C. We did C = 1 and C = 2. One reason that I focus especially on C = 1 and C = 2 is that there, the mathematicians have worked out very nicely for us the harmonic analysis on the target space moduli space. So for C = 1, that was very simple because that was just a 1-dimensional space. We can take the eigenfunctions by hand. For C = 2, it was 2 copies of H mod SL2Z, so that was also very simple. But for C = 3 and above, the moduli space is more complicated. It's given by this double coset. Okay, whatever, this is just some space. But actually, I could not find any expression in the math literature for some extensive discussion for explicit formulas for the harmonic analysis, meaning the eigenfunctions of the Laplacian of this space. Explicit formulas meaning some explicit expansion into all of their Fourier modes, etc. So we won't be able to give as explicit formulas for higher C, but but we're able to reduce this to just a math question, which is that if some mathematician hands you the eigenfunctions forming some orthonormal basis for functions defined invariant under this, we can say what the central charge C in Narain theories decomposition is, and it's given by this expression. And let me say what it is in more detail. So here I write the expression again. So there's a lot of moving pieces, so I just want to go through them slowly. The first thing we can do is we need to subtract out the average over the target space. This is, by subtracting this out, then we're going to compute not the decomposition of the Narain theory, but rather deviations from the average. Now, we also then need to compute three pieces: the constant, the Eisenstein piece, and then the cusp form piece. The constant piece will just be an Eisenstein series, not for SL2Z, but for OCC. And this has a very nice interpretation now as not the average over the target space, but the average over the worldsheet. And there was actually a lot of extensive, beautiful work by, I think this is just three of the three papers, but there are probably many others, where in fact they used this harmonic analysis technology to compute the average over the worldsheet. And their motivation was from some string compactifications, because in string theory, you often need to average over the worldsheet moduli when computing, for example, string scattering and various quantities. Okay, very good. So now there's a single term, which is the average over the target space. There's a term which is the average over the worldsheet. This is just some conventions. And then there will be two infinite combinations of eigenfunctions, a continuous one and a discrete one. There will be some worldsheet continuous eigenfunctions and some target space continuous eigenfunctions, and their eigenvalues will be the same up to a constant shift of C over 2 times 1 minus C over 2, which is precisely what you get from this differential equation. There's some conventions here. Similarly, there'll be an infinite series of discrete eigenfunctions with random sporadic eigenvalues under SL2Z. And there must be, by the differential equation, there must be an infinite series of discrete eigenfunctions for the target space coordinate. Unfortunately, I don't know any math discussion of these discrete eigenfunctions, but one interesting thing from this decomposition is we're able to make some math prediction. I'm sure they're aware of it, but for any value of C, there must be an infinite series of discrete eigenfunctions where the eigenvalues are intimately related to the eigenvalues for SL2Z. So you take the SL2Z guys and then you just add some particular shift, and then they must show up in some correlated way for the decomposition of the Narain CFT partition function.
Nathan.
Yes.
Where did you say the worldsheet average came from? Was that one of the inner products, or is it to make it converge?
Yeah, I actually didn't say that this is the. I didn't show that, but actually here's an easy way you can see that this is the worldsheet average, which is this is just some constant as a function of the moduli, and now we can very clearly see that it's the worldsheet average. Let's integrate over tau. These Eisenstein series are all orthogonal to the constant. So when you average over tau, this term vanishes. These ES's also vanish, and also this EC over 2 vanishes. So the only thing you get left is here. By the way, this also gives a very nice interpretation of your work, Nima and Alex and Ed's work, which is it's also very clear from this decomposition why this first term is the average over target space, because these target space eigenfunctions are all orthogonal to the identity, because the identity is going to be one of the eigenfunctions of the Laplacian of this target space Laplacian. So if we average over M, which is my coordinate for the moduli space, this term obviously survives, but this curly E will vanish here, this curly E here will vanish, and this term here is you can think of it as an OCC version of mu, and that should also be. Although I haven't said this even written down, that should also be orthogonal to the identity. So this term should also vanish. And so we see explicitly that this is the only one that survives when doing the average.
I understand. I guess what I was asking was you outlined a procedure for decomposing the partition function, which was you subtract a piece that won't converge in the inner product, and then the rest is basically just take inner products. You will end up with a continuous piece and a discrete piece.
Right.
This third term in
Oh, yeah. So here you take the inner product with the number 1.
With the mass from.
Well, it's just a constant. Just the constant.
Yeah. Oh, I see.
Yeah.
Sorry. Okay. Thank you.
Yeah. Thank you. Okay. Very good. I guess I lied when I said that I was just going to be an hour. Sorry. Maybe I'll just keep going for now, and people can of course leave whenever they want. So there are many interesting lessons you can learn from this spectral decomposition. And one thing I want to point out is that if you have the explicit decomposition, you can read off some interesting properties such as the scalar gap. So by scalar gap, I define this to be the lightest non-vacuum scalar operator. And an interesting question is, what is the scalar gap as a function of the target space moduli? And this information is all encoded in the analytic properties of this overlap function here. Okay, of course it has to be encoded because this is the full spectrum, so you should be able to read it off. But I think it's kind of illuminating to see how it's read off. The scalar gap is quite interesting because, well, it was recently shown by Nima and Tom and others that as Amir and others that the average scalar gap for a Narain CFT at large C actually scales with C, which is kind of interesting because if you had an analogous statement for Virasoro that the average gap scaled with C, that would be kind of a theory of what people sometimes call pure gravity, where a low energy observer would just see some boundary gravitons and wouldn't, and the first non-trivial state would be maybe have some interpretation as a black hole. And it would be interesting to understand these Narain theory gaps as sort of a warm-up. But let's just investigate what the scalar gap would look like as a function of the moduli. So if we have this decomposition, it's very easy to compute the scalar gap because we just take the scalar component of this right-hand side and the customers all go away because they don't have scalars. And then we can just integrate from 0 to delta, and that'll just count the number of states. And we can see when this integral is not equal to 0, and that'll tell you about the gap. So let's define this quantity and not of delta to be the integral from 0 to delta of the scalar density of states. I subtract off the delta function for the vacuum. In terms of these overlap functions that we've computed, we can get an explicit expression. And if you work it out, you get this expression here. Okay, the details don't really matter, but there's some expression you can get here. And the strategy now that I want to use is the fact that suppose the scalar gap is some number 17. Okay, so suppose there are no scalar operators with energy less than 17. That means if this delta is like 16, then you better get 0 on the right-hand side for this n naught of delta. So in other words, for any delta less than delta gap, the integral from 0 to delta of the density of states should be 0. And we have an explicit expression for n naught of delta, and we can do some contour manipulations to see whether or not it vanishes. And okay, I rewrite it again here, and I'll spare you the details, and I'll just tell you if you do some contour manipulations and cancel off the first two terms here, you can show that in order for this expression to vanish, then FC, this overlap function, which I call F here, needs to fall off as delta gap to the minus S at large S. Okay, so maybe that was a little bit fast, so let me just do an example, and I think it'll be clear. So let's look at C equals 1. And for convenience, let's choose a t-duality orbit to label the moduli by. So the t-duality orbit I'll choose is the coordinate r from 1 to infinity. So that's some t-duality orbit. In this coordinate, we've explicitly computed this overlap, right? This was this r to the 2s minus 1 plus r to the 1 minus 2s that we computed by integrating the lattice theta function against the Eisenstein series. And we can just take this expression and compute it at large S. And it scales as r to the 2s. And I was saying that the gap that this expression must scale as 2 times the gap to the minus s. So if r to the 2s scales as 2 delta gap to the minus s, that means the gap is 1 over 2r squared. So just from the analytic properties of the overlap function, we can read off the gap in the scalar sector. And we can also see where this is maximized. This is clearly maximized when r equals 1, which is the self-dual point. Okay, let's do another example. Let's look at C equals 2. again, we've computed the overlap with the Eisenstein series. And then if you just go through algebra, if you choose rho and sigma to be in the usual fundamental domain, then this expression here is just the imaginary part of rho times the imaginary part of sigma to the s. If you set this equal to the formula we have for the gap, that means the gap is 1 over twice the imaginary part of rho times the imaginary part of sigma. So this is very nice. That means that if you tell me any c equals 2 Narain theory, I can immediately tell you what the gap is in the scalar sector just from this formula. And if you want to maximize the gap, that means we want to minimize the imaginary parts of rho 2 and sigma 2. And those are minimized at this Z3 symmetric point. And that's at square root of 3 over 2. So if you plug in square root of 3 over 2 for both of these, you get 2/3. And indeed, this is a known fact that the c equals 2 theory with the largest gap has a gap of 2/3, and this is like I think this is the SU3 level 1 WCW model. The only point I want to point is that there are some nice cool applications you can use to understand things like the gap, and I think it would be very interesting if we can understand the gap more generally, especially for the Virasoro case.
Sorry, f of s was the contribution of the continuous piece?
Yeah, that's right. That's right. The overlap with the continuous piece. So the integral of z with Eisenstein.
So the discrete bit has no bearing on the gap.
The discrete has no bearing on the scalar gap. So there's a reason I focus on the scalar gap, which is that if you remember these discrete guys, they have no scalar component. They only have spinning component.
Right, right.
So if you focus on scalar gap, you don't have to worry about it. Actually, I think it would be very interesting to look at the gap in the spinning sector, because then you would have to deal with the discrete guys. And that's maybe a little bit daunting, but I think it would be very interesting because the discrete guys are going to be very, very important in order for the spectrum to be discrete. I think it would be very interesting to understand that better.
Thanks.
Okay, so in the last part of my talk, I'm going to move on to general 2D CFTs. So maybe is a good place also to stop for questions if there are any. Okay, so far we've been studying the spectral decomposition of Neuron theories. These are a very, very special class of theories where the central charge is same as the asymptotic growth of the chiral algebra. So let's study a generic 2D CFT. So I'm going to define this to be one with central charge bigger than 1 and only Virasoro symmetry. So because there's only Virasoro symmetry, the sort of best thing I can do for counting the primaries is defining this primary counting partition function, which I call ZP. So this soaks up all of the Virasoro descendants. Okay, there's some subtlety about null states, but whatever, let's not worry about that. And now you can ask, well, can we decompose this guy in terms of the spectral decomposition? Now, at large y, this is very divergent. This is exponentially divergent, as opposed to just polynomially divergent when we soaked up all of the chiral algebra in the Narain case. So we're in sort of fundamentally much worse, like fundamentally different and worse shape than we were in the Narain theories. In the Narain theories, when we soaked up the descendants, we just got a power law divergence, and that we can deal with by subtracting an Eisenstein, which we interpreted as the average. Here we have an exponential divergence, so we'll need a different trick. So why is it that we have this exponential divergence? So in general, let's consider the contribution to this primary counting partition function for some operator with dimension delta and spin j. This will contribute like this effect here, where this C of minus 1 over 12 comes from the Casimir shift of the operator, because we're putting it on the cylinder. So somehow all operators with the total conformal dimension less than or equal to C minus 1 over 12 are sort of badly behaved, and they're messing us up. So we need to remove them all in a modular invariant way to make the function square integrable. So as a cartoon, here I plotted H and H bar. So here's the vacuum, and all operators in this triangle regime are sort of like they're the badly behaved ones. They're sort of in the danger zone. So any operator here will give us something that's exponentially divergent, but any operator outside here is exponentially decaying at large y, so it's very, very safe to include. So somehow we need to remove all of these operators here. Fortunately, there's a very nice prescription that we can do it. And there were various papers, the first one by Maloney and Witten, which basically they did other things, but the salient thing is I'm just going to tell you they did the following algorithm. Give me any operator in this triangular regime as an input. That operator by itself is not modular invariant, but then they do a sum over its SL2Z orbit and something called a Poincare or sometimes a Rademacher sum. And what that will give you is a modular invariant function where all of the output are in this square region here. And you'll notice that this output is all outside of this dangerous triangle regime. So what we're going to do is we're going to take the finitely many operators in this triangle regime. We're going to take their Poincare sums, and we're going to subtract that from the partition function. And that will render it square integrable. So this is just what I said. I'll say it again. We subtract off the Poincare sum of finitely many operators, which are light, and that will give us a square integrable function. I want to comment that this is actually, in a sense, exactly what we did in the Narain case. There, the analog of C-1/12 is 0, because this 1 comes from the one Virasoro copy of Virasoro we have. For the Narain theories, there are C copies of U1. So there, we subtracted out all operators that are less than or equal to C minus C/12, which is 0. The only operator with dimension less than or equal to 0 is the vacuum. So we subtracted out the Poincare sum of the vacuum, which was precisely this average guy right here. And the rest was square integrable. So for the Narain case, we took the partition function, we subtracted out the Poincare sum of the light operators, which had a beautiful interpretation as the average, and then we did a spectral decomposition here. So now, what I'm proposing is that for a general CFT, we do the same procedure. We take all light operators. There may be many of them, but there will always be finitely many of them. We take their Poincare sum and we subtract it out. For the Narain case, the Poincare sum had an interpretation of the average. It would be extremely interesting if for a general CFT, there was also an interpretation as an average, but this is much trickier to say because what are you averaging over? Because a general CFT doesn't have any marginal operators. Note, by the way, a subtle point also, which is that if it is to have an interpretation as an average, there must be some sufficiently light operator. Otherwise, because we're summing only a finite number of operators, you can show that the sum will not be positive definite. Unfortunately, here's the part where I'd like to give some examples, but unfortunately, I don't know of any examples of C bigger than 1 Virasoro CFTs with no extended chiral algebra. So instead of examples, I will use this technology to prove one non-trivial theorem about 2D CFTs in general that I personally don't know of another way to prove this, and I'm hopeful that this theorem can be approved upon. So we can prove a new notion of what's sometimes called spectral determinancy, which is the minimum set of operators needed to fully determine the spectrum of the full theory. So here's the statement. The entire spectrum of a 2D CFT is uniquely fixed by all light operators, which have dimension less than C-1/12, all scalar primary operators, and all spin 1 primary operators, where I can replace spin 1 with any spin, spin 17. So in pictures, so here's a plot of the dimension on the x-axis and the spin on the y-axis. All operators lie below this unitarity bound. The point is that if you tell me all operators first in this triangular regime and all spin 0 and spin 1 primary operators, then that determines the rest of the spectrum. So if you tell me the blue guys, everything else is fixed. Okay, so I put the picture here. And the proof is very, very simple using this technology. So the proof goes as follows. I can even explain it just in words. Let's assume there are 2 different partition functions, 2 different spectra that have that agree everywhere in the blue region. Now let's take the difference of those 2 spectra, and the difference by definition does not have any guys in this triangle danger zone. So the difference is square integrable, which means that the mathematicians have promised us that there is a unique decomposition of the difference in terms of the basis vectors of the Eisensteins, the cusp and the constant. Moreover, the difference doesn't have any scalars and doesn't have any spin 1 operators. It turns out, so now I'll tell you this fact, and if you're interested, I can tell more, which is that the scalar part alone is enough to determine the overlap with the Eisenstein series. Given that the scalar part vanishes, that means that the overlap with the Eisenstein series must vanish. Once the Eisenstein series parts vanishes, then any fixed spin is also enough to tell you the overlap with the cusp forms. and we assume that that fixed spin, spin 1 in this picture, vanishes, which means that the overlap with the cusp form also vanishes. And also the constant is a scalar, and if the scalar difference vanishes, then the constant part also vanishes. So therefore, their difference has a coefficient of 0 in front of all of the basis vectors, which means that the difference is 0. So therefore, the two partition functions must exactly match. Okay, you might say this theorem is not that surprising because it's quite a big ask to ask for all these infinitely many primary operators of spin 0 and spin 1. But I actually personally don't know of a way to prove this theorem without this technology. I also think it can perhaps be strengthened, which is that if one was able to classify which linear combinations of these Eisensteins and cusp forms allow for a discrete inverse Laplace transforms, then I think this theorem can in principle be sharpened. And it might even be useful to constrain theories of pure quantum gravity under some definition of pure. So I think this could be a very, very interesting future direction to think about. Let me just wrap up with some future directions, and then I'll take more questions if that sounds good. So the future directions. Okay, can we use this technique to bound the gap as a function of the central charge, either for the Narain case or the Virasoro case? So as an example, I looked at the scalar gap at c = 1 and c = 2. Can we do this in general? Can we put some interesting bounds on the scalar gap? Okay, how can we efficiently use the fact that the spectrum is discrete? Most combinations of the basis vectors will not lead to a discrete spectrum, and it would be very interesting if we could somehow use this to our advantage in this spectral decomposition. Okay, the third one is with this spectral decomposition, in principle, we can compute powers of the partition function at all points in the Narain ensemble. And recently, this was done for a sort of a baby version of the SYK model by Saj, Shanker, Stanford, and Yao. And they found some interesting saddles that resolve some puzzles about, or shed light on some puzzles about factorizability. And it'd be interesting if there's some analogous statements of these so-called half wormholes for these Narain ensembles. Okay, is there any interpretation of averaging in the Virasoro case? And I want to now say two more future directions that I think are quite interesting, and they specifically talk about these cusp forms, these random discrete eigenvalues, eigenfunctions. So first, recall the Fourier decomposition of these cusp forms. There was some functional dependence, which was fixed by the differential equation, and then there were some random sporadic numbers. In fact, the mathematicians have conjectured with extremely good evidence that these random numbers have fixed statistics, and in particular, if J is a prime number, then they obey a semicircle law. So they're always between -2 and 2, and the probability of the value is a semicircle law. And this is just wild speculation, but it would be very interesting if there was some CFT interpretation of this distribution, because of course this semicircle law is shown up in other contexts. Of course, it could just be a red herring. So okay, I don't know. I don't know if there's any CFT interpretation of this. Maybe as a signature of chaos of the CFT spectrum. And the second thing I want to talk about these cusp forms is related to what Nima asked about looking at not the scalar gap, but the spinning, the spin 1 gap, for example, which is that the spectrum of the CFT is discrete. For the scalar sector, this discreteness comes solely from the Eisenstein series. But for the non-zero spin, the cusp forms play an important role. So let's look at c = 2 as an example. So here's the spectral decomposition of c = 2. Now let's suppose I look at the spin 1 sector. So in the spin 1 sector, this last term will contribute. And we know that the spin 1 sector, if you take the inverse Laplace transform, is a sum of delta functions with some lattice spacing. But it's very, very interesting because these cusp forms are so random and chaotic that if you take one of them and you change the 10th decimal place by just one number, right? The mathematicians are computed to 1,000 decimal, just change one decimal place, and then you take the inverse Laplace transform, you will presumably spoil your discreteness. And it seems very interesting to me that somehow, like, if you didn't know about the cusp forms, if you just took this expression but crossed off the final line, you would get a spectrum that's perfectly healthy and discrete in the scalar part. But in all of the non-scalar parts, you would get this continuous spectrum. And only when you include the cusp forms do these continuous spectrums get resolved into a discrete sum of delta functions. And I think it would be very worthwhile to understand that more and see if that can teach us general lessons about the discreteness of the spectrum in general 2D CFT. Okay, with that, I'll stop here and take questions. So, but thank you all very much for your attention.
Thank you, Nathan. Thank you for the wonderful talk. Question from the audience, please.
I have a question in the slide of future directions. If we can go back to, yeah. So about the first icon, what do you have in mind exactly? So for the Narain case, do you mean just the ordinary Narain CFT? In that case, we since there's an explicit formula for the spectrum, is it difficult to? Yeah, I mean, we know
I think
the gap should be, right?
Yeah, well, maybe Nima can comment more, but this is my understanding, which is kind of surprising, which is that, so okay, so first for the Narain case, I mean, gap under U1 to the C, of course. But for the Narain case, based on work that I guess of Nima and friends, we know that we know what the average gap is for any value of C. And it is true that, of course, as you say, we have the lattice data function. So you can ask, like, why can't we just compute the gap? But I think bigger than like 8 or something, it's not even known how to like optimally search the space of this target space moduli space and find the optimal gap. So I think it's an open problem what the optimal gap is for Narain theories for central charge bigger than like, I don't know, 4 or 8 or something like this. Even though we have explicit formulas, because these explicit formulas, I guess the problem is maybe they're just, it's just very hard in practice to find out what the optimal gap is searching all of this non-compact moduli space.
But in principle, it's a calculus problem, right? In principle, it's not a finite.
Well, I think it's not just a. I mean, even at a fixed point, because for general momentum and winding modes, you can get cancellations. Like, suppose you search like the first like 100 vectors. Is it obvious that like the next vector you search won't have a lighter state? For C equals 1, it is, because for C equals 1, increasing momentum and winding only increases the energy. But for higher C's, that may not necessarily be the case. So yeah, I don't know if Nima, you wanted to add anything to that, or
no? I think in general, it's hard to parameterize the lattices and try to minimize the gap. This is essentially, I think, the same as the sphere packing, which is, as you know, is not optimized for a dimension.
Yeah, to maximize the gap. I mean. Right.
Yeah, to maximize the gap. Yeah.
Huh. So the general C answer is not known. Is it saturated by some rational CFT, rational point?
I think it should be saturated by a rational point, but interestingly, I guess based on this averaging work of Nima and others, the average answer is known, but not the and I guess it's conjectured that maybe the optimal value is the same as the average into large C limit, but I don't know of any proof of this statement. It's kind of funny that in some sense, the optimal regress bound for Narain gap and Virasoro gap is the same, because for Narain gap, we've classified all of the theories, and in Virasoro, we've classified like none of the theories. And it's very funny and counterintuitive that even though our understanding of the space of these theories is at diametrically opposite poles, our rigorous proof of the optimal gap of them is basically the same, like C over 9 point something for them both, or whatever.
Interesting. I have a second question.
Yeah, go ahead.
So in this spectral decomposition, you have an integral over the this S, right? It's along the imaginary axis at real value 1/2. Is there anything useful one can do to deform the contour to one side or another?
Yeah. So indeed, when I discussed, so I went through this a little bit quickly, but when I discussed it's fine. When I discussed this scalar gap here, in order to derive this last formula here, I had to deform this contour to large S, and then that gave some condition on the fall off. That gave some condition relating the gap to the fall off rate of FC of S at large C. And there's also some poles in this overlap function needed to cancel. There has to be a pole at S equals 1 to cancel this term here.
Is there some positivity on the residues for the overlapping function?
Let's see.
Because for 4-point function, in the conformal partial wave expansion, the residue will literally become the OPE coefficient squared.
Right.
Here it's not
right.
obvious because even when you deform it, these are not characters.
That's right. That's right. I think there probably should be some. Maybe it's not obvious to read it off, but I guess there should be some positivity or some kind of positive things when you work hard and convert this expression into something like the characters. But I'm not sure what it explicitly is and if it's in practice useful.
Right. Okay. Okay.
That's something related to that. Is there any sense in which these inner products are well defined when taken with not a modular invariant function? For example, characters with sufficiently good fall off. I mean, the answer on the right-hand side will necessarily be modular invariant because you're expanding in terms of Eisenstein and non-forms and so on. But
yeah, that's a very good question. One complaint, I mean, this is maybe a too technical of a complaint, but one complaint I might have is that when I define the overlap, I integrate over this fundamental domain. And the only reason I integrate over that is that the function is modular invariant. Maybe for the characters, you could try defining it, maybe integrating over the strip or something like that.
mm-hmm.
I'm not sure. That's a good question. I don't know. I don't know of any way to make it well defined, but maybe there is one.
Well, I would imagine because the sum over characters
right.
is modular invariant, as an intermediate step, perhaps like the expanding the characters in terms of these functions, because those things will have integer coefficients is one way of inputting.
Right, but you will never be able to expand the characters exactly in terms of these functions, because if you expand these in terms of these functions, it'll be modular invariant, of course.
Does the inner product not commute with the sum over characters? If I write the partition function.
I see what you're saying. I see what you're saying. You're saying take Z, compute the overlap of Z with the Eisenstein. That's well defined, and now try to move that into the sum.
Yeah, basically.
Oh, I see what you're saying.
The subtlety of subtracting the light stuff, but I don't know how to deal with that. But
yeah, okay. Let's not worry about the subtlety for now. Yeah, that's interesting. I mean, okay, I guess it would be I see what you're saying. I see what you're saying. You're saying, okay, forget the fact that you're quote unquote not allowed to do it. If you just move the integral inside the sum, you may get something interesting.
Yeah.
Oh yeah, that's actually very interesting. Yeah, we didn't think about that. That's quite interesting.
Nathan, can I ask a question?
Yeah, of course.
So this may be a little vague, but conceptually, can I think about what you're doing as kind of unaveraging the average dependent functions? For example, the ones coming from EC.
Yeah, absolutely. Yeah. So
and then a follow-up question would be I mean, there's this nice interpretation of this Eisenstein series as the dependent function of this transimus-like theory in ADS. Well, transimus-like theory in the three-dimensional bulk. And is there a similar interpretation for the mass forms? Perhaps for the same transimus theory, but with respect to a different integration contour?
Yeah, so your first question, absolutely. So we're sort of computing the deviations of the average. So you can say it's like unaveraging. For your second question, if there's some Chern-Simons-like interpretation for the cusp forms or anything like that, I have no idea. That's very interesting, but I have no idea.
I see. But it sounds logically it could be just a different choice.
I think so.
Contour.
Yeah.
And you want to kill all this scalar contour.
Exactly, and somehow they cancel when you do
exactly
the average or something. Yeah, I think it could be, but I have no idea.
And this could be related to this observation that you made about this coefficient in the cusp form that has this semicircle distribution.
Why do you say that?
Because this is kind of like I mean, this semicircle law shows up in some kind of holographic setups. I'm
I see.
Sure what's the interpretation of this. But if you have a Chern-Simons interpretation, if you do have a Chern-Simons interpretation of this this function, then there could be some insight towards why such objects, why such coefficients.
Yeah, that's interesting. Yeah, thanks for the comment.
But this eigenvalues, do you see any physical interpretation of these eigenvalues for the Laplacian?
The eigenvalues, no, the eigenvalues aren't the ones that have the semicircle law. It's the coefficients.
I know,
yeah,
but
the eigenvalues, I don't know. I mean, the eigenvalues will grow like this. There's this Weil's law, so they grow like, I don't remember, like square root or something like this. But yeah, I don't know any physical interpretation. Right?
Mm-hmm. Thank you.
Yeah, thanks.
Just curious, on this particular slide, I wonder if you change C equal to 2 to C equal to 3, is there something you can comment about this?
Yeah, actually I can. I didn't talk about it in the talk, but so C equals 3, I need to do the full, so okay, I could give you the abstract formula, but that's not very useful. But for C equals 3, so there's a 9-dimensional moduli space now, and I don't have an explicit expression in terms of all 9 dimensions of these moduli. But if you look at some sub-loci, I can give you the answer. So for example, a sub-loci of these 9 dimensions is when the C equals 3 theory is a product of C equals 2 times C equals 1. So that'll be some, that'll have like, I guess, four moduli from C equals 2 and 1 moduli from C equals 1. So that'll be some 5-dimensional sublocus of this 9-dimensional moduli space. And on these product subloci, if you take a decompactification limit, meaning you take one of the tori to be very, very large, then I can give you the answer to all orders in perturbation theory. So that's in the paper. You can look up the formula. Interestingly enough, there seem to be similar 8s showing up there too for the cusp forms. I have no idea why. But yeah, I don't know of a general, but anyways, just to answer your question, I don't know of a general formula for C equals 3 or above, but in some specific special loci, like when you take a product locus and take one of the tori to be very large, then I can do the computation.
And I think most of your talk maybe focus on conformal symmetry of the CFT, which is a space-time symmetry. I wonder whether you know, like when you write down some CFT, are you able to implement additional internal global symmetry? Like there may be some additional structures. For example, which maybe you just show this partition function, maybe there's some additional discrete. I don't know whether I'm making sense. But
right. I mean, I guess here is a symmetry of the spectrum. I don't know. It's not a necessarily symmetry of the quantum field theory because this is going to be mixing the worldsheet target. But here there's a symmetry. There's an S3 symmetry where you exchange any of these parameters.
Right. So my point is that whether this maybe particular constraint on the partition function may relate to perhaps this CFT can implement additional internal global symmetry.
Right. So this S3 is a little bit different because again, the symmetry is mixing like different quantum field theories, right? If I change rho and sigma, that's a different quantum field theory. But yeah, I guess in general, you're like, I think it could be the case that like doing this kind of decomposition may make some symmetries manifest.
Actually, I think I can reinterpret Juven's question slightly differently. So this S3 is not the internal symmetry of the CFT, as you said. I think Juven was wondering for CFT with some internal symmetry, maybe Z2, U1, etc. Can we run this this game in a more general way? So let's say it's a Z2, right? So then we will not just have one single partition function, but we will have a vector value partition function, and then they transform in a certain way under SL2Z. And maybe there's some similar spectral decomposition for this vector value.
Oh, I see. I expect there is. Yeah, that might be interesting to work out.
Right.
Sorry, can I get back to this the potential bulk interpretation of your partition function again?
Yeah, for sure.
So this S integral and the sum over this ends for the mass form, can I interpret as some kind of part of a gravitational path integral? Like in the JT case, you have, when you compute like Boolean this, well, not Boolean, but when you compute the partition function of the trumpet, you have the integral over this moduli that's associated with the size of the geodesic. Like when you compute partition function with multiple boundaries, additional. So this is kind of more transparent for the C equal to 2 case. I don't know how to interpret the higher C cases. It looks like some kind of a multi-boundary partition function if you want to try to interpret it from the bulk perspective, like with 3 torus boundaries.
Right. But by the way, there should be. In principle, one should be able to also do I don't know in practice how to do it, but once you be able to do, multi-boundary, like higher genus, whatever,
right.
yeah, as well.
Right.
So it's some spectral decomposition. But okay, we can focus on genus 1.
Yeah, I was just wondering if if the meaning of
S I see.
is related to some kind of
yeah,
some kind of moduli from the gravity perspective
that
you should integrate over.
Yeah, that's interesting. Yeah, okay, yeah, that's an interesting comment.
Yeah, it's certainly not something physical from the if you just give you the CFT, but if there's a gravity interpretation, then
right.
It's supposed to have an interpretation as a moduli within the gravity.
Right. Yeah, thanks. Yeah, thank you. That's very interesting.
Can I ask also, with the semicircle law that you mentioned in your future directions, that was the distribution of the coefficients of the model. Is that right?
That's right. Well, so it's funny. It only tells you the distribution of the coefficients of the prime spins. The composite ones are uniquely determined from the prime ones. But yeah.
Is there the higher moments? Are they?
I think there is, but I don't.
Is it like known that they're RMT like or anything like that?
I think there's a statement something like that, but I don't know the precise statement. Actually, this statement I wrote here only works at large J. So at finite J, there's a different expression, and this is what the simplification at large J is. I think the higher moments do have some RMT-like statistics, but I don't remember off the top of my head. But the thing to Google is this Sato-Tate conjecture.
Cool.
Yeah. So it's kind of tempting to speculate wildly.
Yeah.
Any more questions? Let's thank Nathan again. Thank you very much, Nathan.
Hey, thank you very much.
People can still stay more questions.
Thank you. That was a beautiful talk.
Thank you.